In the last video, we talked about how researchers have tested the CAPM in reality. Today, we're going to focus on implementing those tests in Excel. An important skill that you need to develop, whether you work in investment management or whether you work in corporate finance, is to be able to estimate market risk. And we said that we would estimate market risk, or beta, using what we call the market model. And we will run a regression where the dependent variable are the returns on Merck and the independent variable are the returns on the market. When we run this regression, beta, which will be estimated, is our measure of market risk. In other words, how does Merck respond to a change in market returns? Estimating betas is actually very simple in Excel, so let's do that now. In this spreadsheet, we have data for the S&P 500 and for Merck. And in columns E and F, I have calculated Merck's returns and the S&P 500 returns. What we now have to do is run a regression. To run a regression, we need to load the analysis toolpack into Excel. To do that, go to the Office button, and at the bottom, select the Excel options. Now go to Add-ins, and it will list all the add-ins that you currently have up and running in Excel. Now here, you can see I have the analysis toolpack running already. But suppose I didn't. What you need to do is go to the Manage Excel Add-ins, click Go, and up pop the options that you can add in. And we can add, if you haven't selected them, please select the Analysis Toolpack and the Analysis Toolpack VBA. Click OK, and now you should see a Data Analysis tab if you go to the Data tab at the top. Once it's loaded in the Analysis Toolpack, you should see Data Analysis on the far right hand corner. Select Data Analysis, and if we scroll down these options, we want to select Regression. Click OK. Excel now prompts us to input the Y range and input the X range. The Y range is the dependent variable. That's going to be Merck's returns. So if we click on the box here, let's select Merck's returns. The X range is going to be the S&P 500 returns. That's our independent variable. We want to output the analysis to a new worksheet, and we'll call that worksheet Beta. To run the regression, we just click OK. And Excel automatically creates a new worksheet with the regression results in it. We have some summary regression statistics at the top. We don't need to worry too much about these statistics for the time being. What we're interested in are the coefficients. In particular, what we care about is the slope coefficient. That's going to be our beta estimate. Based on the regression we've just run, the estimate of the beta, so the estimate of market risk for Merck, is equal to 0.85459. And if we look across, we have lots of useful information about this estimate of beta. We have the standard error, and the standard error, remember, reflects the uncertainty there is about our estimate. We also have some information labeled lower 95% and upper 95%. What these two bits of data mean is that there is a 95% probability that the true value of beta for Merck ranges between the lower value and the upper value. In this case, there's a 95% chance that the true value of Merck's beta is between 0.33 and 1.37. That implies there's an awful lot of uncertainty about the true value of the beta for Merck. Does this matter? The answer is yes. If we go back to PowerPoint, to calculate the expected returns for Merck, we need to have the risk-free rate, which we're going to assume is equal to 4%. We need to have the beta for Merck, and we know that is going to be equal to 0.85. And we need to have the expected annual market risk premium, which we think is about 8%. With all these numbers, we can now calculate the expected return for Merck. And that's going to be equal to the risk-free rate plus beta times by the expected market risk premium, which gives us about 10.8% per year. So if Merck was thinking about making an investment in a project, the discount rate they would use that reflects the riskiness of that project is likely to be around 10.8% per year. But now remember that we're quite uncertain about the true value of the beta for Merck. The 95% confidence interval ranges from 0.33 to 1.35. This translates into a 95% confidence interval in terms of expected returns of 6.6% all the way up to 15% per year. There's a huge potential range of discount rates. We can see the 6.6 is obtained by doing 4 plus 0.33, which is the lower bound for our beta estimate, times by 8, which equals 6.6. And the 15% is equal to 4 plus 1.35 times by 8, which is approximately equal to 15. So there's a word of caution whenever you are calculating discount rates or thinking about expected returns. When you use an estimate of beta, there is often considerable uncertainty. And remember that when you're thinking about discount rates or thinking about expected returns from a stock going forwards. Now let's turn our attention to testing the CAPM. In the last video we talked about 2 tests of the CAPM, but we're only going to focus on the second test in class. We're going to ignore the first test because there are an awful lot of statistical difficulties there. And rather than do a poor job testing the CAPM, we're just going to ignore the cross-sectional tests in this class. Instead, we're going to focus on implementing tests for the time series approach. Now recall, the time series approach involved running a regression for each stock or portfolio of stocks, and the regression is specified here. We need to look at the excess returns on a portfolio or a stock and regress those on the excess returns from the market. What we're testing is the intercept. If the CAPM holds, the intercept, or alpha I, should be equal to 0. I want to test the CAPM for the exact same data that Fammer and French looked at in their 1993 paper. That would involve running 25 regressions, because Fammer and French used 25 different portfolios. If we went through and ran a regression the way we just did to estimate betas for Merck, it's going to take a long time to find the results. But there are some useful shortcuts in Excel that you need to learn about. The first shortcut is a function called LinSES. And LinSES effectively runs a regression. You have to input the y's So the dependent variable, the x's, the independent variable. Then you have to specify whether you want a constant in your regression. If you leave it blank, a constant will automatically be included. You then have to specify whether you would like statistics associated with the estimate. If you only want the coefficient estimate, you type 0, but if you also want the standard errors, you must type 1. This is a quick way to run a regression. The problem with LinSES is that it stores the output in column vectors. There's one column for each independent variable, and one column for the constant if a constant is specified in the regression. The trick to remember is that the parameters are listed in reverse order. The constant will always be in the last column. Logically, you'd think the constant would be in the first column. In fact, in Excel they reverse it. Just remember that, it's very important. LinSES is one function that's useful to help us test the CAPM. A second function that is also very useful is the index function. The index function allows us to access components of the column vectors created by the LinSES function. We want to access, for example, the value of the intercept and the standard error of the intercept. To do that, we use the index function. And the first argument for the index function is array, which means you have to tell Excel where is the vector or the matrix that you want it to look at. And then you have to tell Excel which row number do you want to go to and which column number do you want to go to. Here's a simple example before we go to Excel. Suppose we regress excess stock returns for stock A on excess stock market returns. We want the value of the intercept and its standard error if we're going to test the CAPM. To calculate the value of the intercept, we're going to have to run our regression. To run the regression, we use our LinSES function. Here we have our stock returns, or the excess returns for stock A. Here we have the excess returns for the market. That's our independent variable. The next feature is to specify whether we want a constant. We've left it blank, which means we do want a constant in the regression. That's the intercept. And then finally, we're telling Excel that we do want to see the statistics associated with this estimate. So we type 1. That's the LinSES function. And that automatically creates a matrix that's got 2 columns. And we now want to tell the index function where to look for the intercept estimate. We know that the estimate is going to be in the first row. So if we look at our matrix, we're going to see market, intercept. They're going to be the 2 columns. And in the rows, we're going to have the estimate, and then we're going to have the standard error. We want this number here, which is going to be row 1, column 2. If we want to get the standard error for this estimate of the intercept, we're going to have to look in row 2, column 2. And that's what we're doing here. Now let's go to Excel and test the CAPM. In this sheet, we have data for the 25 portfolios that Fama and French used in their 1993 study. We have some titles along the top to help us understand what we're looking at. In the first 5 columns, we have the smallest firms. And then in the second row we're told that within these small firms we've calculated which ones have low book to market, medium book to market and high book to market ratios. And we've done the same for all different sized firms. And we have 25 portfolios. We also have information about the market returns and the risk-free rate. And the data runs from 1963 through to 1990. We're going to use the exact same sample period that Fama and French used in their original study. When we're thinking about testing the CAPM using the time series test, we know that we need to use excess returns, not raw returns, but excess returns. The data here is raw returns, but we've been given information about the risk-free rate, so we can easily calculate excess returns for the individual stocks or the individual portfolios and the market. To do this quickly, we're going to name a range. Let's select the risk-free rate, and if we go to the name box, let's call that RF. So whenever we want to refer to the risk-free rate, it's going to be RF. The next thing we're going to do after naming the risk-free rate is to name the matrix that contains all our returns, which will include the market returns. So let's select this entire range and call this returns. We're now ready to calculate excess returns, but to keep things clear, let's copy across the names so that everything is well labeled. We want to calculate excess returns for all the portfolios, including the market portfolio. So let's select the range where we're going to want to put all these returns. In the formula bar, we're now going to type equals, and we're going to do returns minus the risk-free rate. Do not press enter. This is going to be what we call a matrix operation, so we're going to press Control, Shift and Enter, and Excel will automatically calculate excess returns for all the portfolios immediately. So Control, Shift, Enter. Excel has now calculated all the excess returns. And you can check this manually if you would like. So, for example, let's take the low portfolio. The excess returns on the low portfolio in 1963 should be equal to the raw return minus the risk-free rate for that same month, and we see we get the same number as we got from our matrix operation. So we have very quickly calculated excess returns for all 25 portfolios, including the market. We're now ready to run our regression. We've got the data in the right format. So let's scroll down. The first thing we need to do is calculate the intercept, or the alpha, for all of these 25 portfolios. We're going to use our index function and our LinSES function. We're going to type equals LinSES. We're going to type equals index, because we're going to want to tell Excel where to look for the intercept, and the then we're going to use LinSES. And Excel prompts us for the Y variable. That's going to be the returns on the small portfolio with low book to market. So let's select those cells. Comma. We now need to enter the known X's. The independent variable. That's going to be excess returns on the market. Let's select those. Comma. Now we need to say whether we want a constant or not. We do want a constant included. That's our intercept. So we leave that blank, so we press comma again. Do we want statistics? The answer is yes, so we press 1. Then we close brackets. That closes off the LinSES function. Now we just have to tell Excel where the index function has to look. And we know that to get the intercept value, we want to look in row 1, column 2. Close the brackets, hit enter, and we now have our estimate of the alpha. We need to do the same for the standard error. So we're going to look at the index function again and the LinSES function. We'll select the Y's. We'll select the X's. We want to include a constant. We want to have statistics. In the index function, we now want to look in row 2, column 2. Close brackets, hit return. We can now calculate the t-statistic for the intercept, because we want to do a t-test. According to the CAPM, the intercept shouldn't be statistically significantly different from 0 if the CAPM holds. The t-statistic is going to be calculated as the intercept minus 0, so we can ignore it, divided by the standard error. So the t-statistic in this case is minus 1.09. We want to repeat this calculation for all 25 portfolios. To do that, we need to first of all fix the market excess returns so it doesn't change as we copy the formula across. Let's use the $sign to do that. And we need to do that for both equations, both the alpha and the standard error calculation. Now we can select these 3 cells and copy them across. We've now conducted the same test that Farmer and French conducted in 1993. Now if you recall, Farmer and French said that it was smaller firms with high book-to-market ratios for which there were positive alphas. Across the top here we can see we're looking at small firms and we want to look at high book-to-market ratios. Look what happens as we start with, so we're in the small firms here. As we move from low book-to-market to high book-to-market, we see exactly what Farmer and French were talking about. The alpha estimate goes from slightly negative to being positive. The t-statistic goes from being less than 2, or the absolute value is less than 2, and as we get to the high book-to-market firms, the t-statistic is greater than 2. If we look at the slightly larger firms, we see the same pattern. The alphas increase as we go to the high book-to-market firms, and so do the t-statistics. If we look at even larger firms, we see the same pattern repeated again. Amongst the largest firms, the same pattern is still there. The alpha coefficients are increasing as we go to high book to market firms. But now amongst the large firms, the T statistics in absolute value are not greater than 2. So for the large firms, it seems the CAPM is doing okay. We can't reject the CAPM. But for small firms, it's exactly like Fama and French said. The CAPM doesn't seem to be working. We've now conducted a time series test of the CAPM. That's all I want to cover in this lecture. See you in class.